Hi, in this video I'm going to derive the equations for apparent wavelength and apparent frequency in Doppler effect. This derivation could be done in two different ways. The first method in which we consider the number of wavefronts emitted during 1 second. The second method in which we consider the number of wavefronts emitted during one period of time. So different books follow one of these methods. I'm going to follow the method where the number of wavefronts emitted during one period of time. Okay, so what is apparent frequency? When there is relative motion between the source and the observer, the frequency of the wave measured by the observer might not be same as the actual frequency. Same way, so the frequency measured by the observer is called apparent frequency. Same way, due to relative motion between the source and the observer, the wavelength measured by the observer also could be different compared to actual wavelength, and the wavelength measured by the observer is called apparent wavelength. Okay, we know that the meaning of frequency, number of waves emitted per second is called frequency, or number of wavefronts emitted per second is called frequency. So during 1 second, the number of waves emitted is the frequency. So if I say the frequency of a wave is f, that means during 1 second, the number of wavefronts emitted is equal to f. Also, you know that the period of the wave, the time taken to complete one full oscillation is called the period of the wave. So the period of the wave and the frequency of the wave are related by t equal 1 over f. So during one period of time, how many waves will be emitted? The number of waves emitted during one period, that is, the number of waves emitted during 1 over f seconds is equal to just 1. So I can say the other way, the time taken to emit one wavefront is equal to 1 over f, or the time taken to emit one wave is equal to 1 over f. I need these ideas in this derivation. Also, we need the outcome of the motion of the observer in this derivation. Say, for example, if the source is at rest, this is the source, it is at rest. Say, for example, us is the speed of the source, which is at rest, and the observer is also at rest, uo, the speed of the observer, uo, also at rest. Then the speed of the wave measured by the observer will be equal to the actual speed. If I say the speed of the wave is c is the speed of wave. So if both are at rest, the wave source and the observer, if both are at rest, then the speed of the wave measured by the observer will be equal to actual speed of the wave. But if the observer moves towards a stationary wave source at a speed uo, then the speed of the wave measured by the observer, c dash, will be equal to c plus uo. The observer is moving towards the wave source. Wave source is at rest. The wave is emitted at speed c. Then the speed of the wave measured by the observer, that is the apparent speed of the wave, is given by c plus uo. Same way, if the observer moves away from the wave source, then the apparent speed of the wave measured by the observer is given by c minus uo when the source is at rest. Then also you should know that the motion of the wave source will never change the speed of the wave. Remember that motion of the wave source. For example, observer is at rest. Observer is at rest. The wave source is moving either left or right, whatever it is, at a speed us. The speed of the wave is c, the actual speed of the wave is c. So observer is at rest, the wave source could be moved away from the observer or towards the observer, whatever it happened. The speed of the wave measured by the stationary observer will be equal to actual speed of the wave. So here I'm going to use these ideas. That is, if the observer moves towards the wave source, the speed of the wave measured by the observer will be c plus u naught. If the observer moves away from the wave source, the speed of the wave measured by the observer equals c minus u naught. That's the relative speed of the wave. But if the wave source is in motion and observer is at rest, the speed of the wave will not be affected due to motion of the wave source. So we are going to use these ideas in this derivation. Okay, as I told earlier, I am going to derive this equation by considering the number of wavefronts emitted during one period of time, that is during 1 over f time. Okay, so I can say like this, initially the wave source is here. This is the wave source. Initially it is here, and it has emitted wavefronts, identical wavefronts in all directions. So I consider the wavefronts emitted in front of it and behind it. I will show the wavefronts emitted just I can draw by using circular wavefronts, but I'll draw it by using straight wavefronts. So the wavefronts emitted by it when it is here will travel same distance on either side. The wavefront emitted in front of the wave source will travel through a length this much. It has gone to this position. At the same time, it has gone to this position also here. So these distances are the same. This distance and this distance are the same. Okay, the first wavefront is emitted from the wave source. Okay, so wave source is moving to the right at a speed us. So the speed of the wave is c. So speed of the wave is c. Okay, I'm going to consider the next wavefront will be emitted at a time of one period from the time the first wave front is emitted. So after 1 over f time, that is after a one period, so you know that t equal 1 over f. So after one period of time, at a one period of time, so the wave source will be somewhere here. It will move to this position. So the wave source has come to this position. So I can say this is at time t equals 0. It emitted two wavefronts. They have traveled. The first wave, the wavefront which is emitted in front of the source has come to this position. The wavefront emitted behind the wave source has come to this position. So this distance and this distance are the same because the waves are traveling at the same speed. So the distance traveled in this distance during one period of time, that is 1 over f time, this distance will be equal to speed of the wave c times 1 over f. So c over f is the distance traveled during 1 over f time. Same way, the distance traveled in this direction also is equal to c over f. Okay, so I'm considering the time interval, one period or 1 over f. The wave source has come to this position now at a time of t equal 1 over f. The wave source has reached this position. So the distance moved by the wave source towards right will be equal to this distance moved by the wave source during 1 over f is equal to the speed of the wave source is us. So the distance will be equal to, speed equal distance over time. So distance equals speed into time. So this distance moved by the wave source is equal to us into 1 over f. That is us over f. Okay. So you know that. So now at this time, it's going to just emit the second wavefront. So it's not emitted, not yet emitted, but we can say it's going to emit the second wavefront. So not yet emitted, it's going to emit the second wavefront. Okay, we know that the distance between the adjacent wavefronts gives the wavelength. Imagine there is an observer, O2, he is at rest. There is another observer, O1. That observer is also at rest. So this observer will measure the wavelength of the wave approaching him. So the wavelength measured by the observer O2 will be this one. That is, I can call lambda 2. The wavelength measured by the observer O1 is this one. The wave is approaching here. This is the first wave. This is the second wavefront just going to emit. So the distance between adjacent wavefront is the wavelength. So observer 2 will measure this as the wavelength. So here I can say the wave source is moving towards observer 2 and it's moving away from the first observer O1. The first observer O1 will measure the wavelength, which is the distance between the adjacent wavefronts, as lambda 2. The second observer is measuring the wavelength as the distance between the adjacent wavefronts, which is lambda 2. Sorry, this is lambda 1. This is lambda 1. Observer 1 measures lambda 1. Observer 2 measures lambda 2. So how much is lambda 1 for the observer 1? For the first observer, observer O1, I can say. So I can say the source is moving away from the observer O1. For him, the wavelength measured by the observer is equal to lambda 1, that is equal to this distance, this plus this one. This is from the initial position. The source has moved a distance us over f towards right. So lambda 1 will be equal to this length c over f plus us over f, that is c plus us over f is the wavelength measured by the first observer. For him, he is stationary. For him, the source is moving away from him. Okay, so but we know that for the wave, when there is no relative motion, the actual wavelength, actual frequency will be recorded by the stationary observer. So c equal f lambda. So f is equal to c over lambda. So for the first observer, lambda 1 is equal to c plus us over, instead of f, I can substitute c over lambda. So that is c plus us over c times lambda. So this is the apparent wavelength for the situation where the wave source is moving away from a stationary observer. Observer O1 is at rest, so he is at rest. Wave source is moving away from him. The apparent wave measured by the observer 1 is equal to c plus us over c into lambda. You know that the numerator c plus us is greater than c, therefore lambda 1 is greater than lambda. Okay, when you consider second observer O2, he also at rest. But for him, the wave source is moving towards him at constant speed us. The wavelength measured by the second observer is the distance between the adjacent wavefronts, that is lambda 2. So I can say for observer 2, observer O2, the wavelength measured by him is lambda 2. Lambda 2 will be equal to this length. So the wave source was initially here. That time it emitted the first wavefront. It has reached this position. Then it moved to the right and it's going to emit, just going to emit the second wavefront. So this length lambda 2 equal this length c over f. That's the first wavefront, the distance moved by the first wavefront, speed into time, 1 period. So c into t, that is c into t equal 1 over f. So c into t, that is c into 1 over f. That is the distance moved by the first wavefront. The source has moved to the right, us over f. So lambda 2 equals c over f minus us over f. So that I can write c minus us over f. But we know that f equal c over lambda. Substitute that one here. C minus us over c over lambda. So c minus us over c into lambda is the apparent wavelength for the second observer. That means this is the apparent wavelength recorded by the stationary observer when the wave source moves towards him. You know that the numerator c minus us is smaller than c, so this will be less than 1, so lambda 2 will be less than lambda 1. So yeah, so we have derived the equations for stationary observer and the moving wave source. Okay, next we need to derive the apparent frequency, the equations for apparent frequency. So when the observer is at rest, okay, so I'm going to derive the equations for apparent frequencies now when the source is moving and the observers are at rest. You know, the speed, the equation V equal F lambda could be used anywhere. So I can say apparent speed is equal to apparent frequency times apparent wavelength. Since the observer is at rest, the speed of the wave measured by the observer will be same as actual speed of the wave. So for first observer, if I use this one, the apparent speed of the wave is c because he is at rest equal to f lambda times lambda 1 dash. So that is lambda 1. I can say c1 equal f1 times lambda 1. Okay, I'll use that way. C1 equal f1 times lambda 1. So c1 is the apparent speed of the wave measured by the observer 1, the first observer. F1 is the apparent frequency measured by the first observer, and lambda 1 is the apparent wavelength. Lambda 1 is this one, so I can say C equal F dash into C plus US over C into lambda. So you know that lambda over C, you know C equal F lambda. 1 over F equal lambda over C. So you can see lambda over C, this I can write lambda over C. So lambda over C equal 1 over F. So I can say C equal F dash times C plus US. Well, lambda over C is 1 over F over F. So from this I can say F dash equal cross multiply CF over C plus US. CF over C plus US. This is the apparent frequency. That is, when the wave source moves away from a stationary observer, the frequency of the wave measured by the observer is given by F1 equal, so I'll put F1, so this is not F dash, I can say F1 equal C over C plus US into F. So that is F1 equal C over C plus US into F. This is the apparent frequency of the wave measured by the first observer. Okay, so for observer 2, the wave source is approaching the observer 2. So for the observer 2 also, I can write C2 equal F2 times lambda 2. C2 will be same as the actual speed because the second observer 2 is at rest. So C2 is equal to C equal F2 times lambda 2, I already derived it, C minus US over C into lambda. This I can write C minus US into lambda over C. Right, lambda over C. So lambda over C equal 1 over F. So that is F2 C minus US over F because lambda over C equal 1 over F. So C minus US over F. So F2 is equal to C over C minus US into F. This is the apparent frequency of the wave recorded by the second observer who is at rest. The wave source is moving towards the observer. You know that here, since the numerator C, denominator C plus US, the denominator is greater than C, means F1 less than F. Here, F2, because you know C minus US is smaller quantity than C, so this fraction will be greater than 1. So F2 will be greater than F. So when the wave source moves towards an observer, the apparent frequency will become larger. When the wave source moves away from an observer, the apparent frequency will become smaller than the actual frequency. Okay, so next we are going to derive the equations for apparent wavelength and apparent frequency when both the source and observer are in motion. So we'll take that observer 2 is moving towards right at speed uO. The observer 1 also moving towards left at the same speed, no problem, uO. The wave source is moving towards the observer 2 as earlier at speed us. Okay, so remember that the apparent wavelength will become different compared to actual wavelength only when the wave source is in motion. Because you can see the diagram. If the wave source is moving from the initial position to the right only, the lambda 1 will not be equal to lambda. The distance between the adjacent wavefronts gives the apparent wavelength. So due to the motion of the wave source, there will be change in wavelength, or the apparent wavelength will become different compared to actual wavelength only when the wave source moves. If the wave source remains at rest, there's no change in the apparent wavelength. If the wave source is at rest, the apparent wavelength will be equal to actual wavelength. Because you know the reason. Because the wave source moves, the distance between the adjacent wavefronts during 1 over f of time or during one period of time will become different compared to the distance between the two wavefronts when the wave source is at rest. That's the reason for change in wavelength, right? So here I told the wave source is moving towards the observer 2. Both observer 1 and observer 2 are moving in opposite directions. That is, observer 1 is moving to the left and observer 2 is moving to the right. So I'm going to get the equations for apparent wavelength and apparent frequency. In this situation, both O1 and source are moving. So no change in wavelength, same as this one. So the wavelength will be same as earlier. No change means there will be change in wavelength. The wavelength measured by the observer will be same as what I derived already. So the wavelength measured by the observer, even he is in motion and the wave source is moving away from his as earlier, so I don't need to derive it again. That will be C plus US over C into lambda. So the frequency measured by the observer will be different compared to this frequency because he is going to measure, the observer is going to measure the speed of the wave differently. The reason, the observer is in motion. So since the observer is in motion, the speed of the wave measured by the observer, I can say for O1 for observer, the speed of the wave measured by the observer will be equal to the speed of the wave is c. He is moving the same direction, c minus uo. You can see the wave is approaching him. The observer is moving away from the source. So the relative speed of the wave measured by the observer, c minus uo. The wavelength measured by the observer, same as the earlier derivation, because that is due to the motion of the wave source. So that will be c plus us over c times lambda. So I can say the apparent speed is equal to apparent frequency times apparent wavelength. And also you know lambda over c is f. I can say that lambda over c is equal to f. You know that because c equal f lambda, lambda over c equal f. I will substitute that later. So now the c1 is equal to, I need to find the f1. f1 is equal to c1 over lambda 1. So f1 is equal to c1, that is c minus uo over lambda 1 c plus us over C times lambda. But you know that lambda over C, this lambda over C, I can put 1 over F, lambda over C equal 1 over F. You know C equal F lambda, lambda over C, lambda over C equal 1 over F. So instead of lambda over C, I can put 1 over F. So C minus UO over C plus US over F. Lambda over C, 1 over F. So that is F comes here. So F1 is equal to C minus UO over C plus US times F. This is the equation for apparent frequency. When the observer moves away from the wave source at speed UO and the wave source moves away from the observer at speed US. He is moving at UO, it's moving at US. This is the equation for apparent frequency. The wavelength in this situation, again, I am saying that the wavelength measured by the observer is same as the earlier thing because the wavelength changes only due to motion of the wave source. Okay, so if I derive the equation for second observer, where the observer is moving away from the wave source and the wave source is moving towards him. Okay, so here also the wavelength will be same as this one because the wavelength is due to the change in wavelength is due to the motion of the wave source. So same as earlier, lambda 2 will be C minus US over C into lambda even when he is in motion. The source is moving towards the observer. So for him, I can use C2 equal F2 times lambda 2 C2. So the wave source is moving towards him and the observer is moving away from the wave source. So here also the C2 is equal to C minus UO because wave is moving towards the observer, observer is moving away. So the relative speed of the wave measured by the observer is C minus, both are in same direction, wave and the observer are in the same direction. So the relative speed will be C minus UO is equal to F2 times lambda 2. I need to substitute this one, C minus US over C times lambda. So F2 will be equal to C minus UO over C minus US over C times lambda. You know lambda over C is 1 over F. I already used that equal to C equal F lambda. So 1 over F equal lambda over C. So this one lambda over C will be equal to 1 over F. So this I can write C minus UO over C minus US over F. So from this I can say F2 is equal to C minus UO over C minus US times F. Okay, so here also will F1, F2 when you compare, which one will be the larger? You know that numerator C minus UO, denominator C plus US. So denominator is larger than numerator because you are adding a quantity in the denominator. So F1 is less than F here. So here I can say F1 less than F. But what is here? What can I say about here? Now I can say in this situation, if UO, the speed of the observer is greater than speed of the wave source, speed of the observer is greater than speed of the wave source, that means you are going to subtract a larger quantity in the numerator than the denominator. Denominator, numerator in both, you are subtracting a quantity U0 and US from the same quantity C. If UO greater than US, that means you are subtracting a larger value in the numerator. So this fraction will become less than 1. So in that situation, F2 will be less than F. The other way, if UO less than US, that is US greater than UO means you are subtracting a larger quantity in the denominator, means you are making the denominator smaller, you are going to divide it by smaller value. So F2 will be greater than F. Okay, so I can summarize like this. The wavelength changes only due to motion of the wave source. If the wave source moves towards the observer, whether the observer is in motion or not, doesn't matter. But if the wave source moves towards the observer, then the wavelength is given by, so you can see the situation, wave source is moving towards O2, the second observer. In that situation, wavelength is given by C minus US over C into lambda. Whether observer is in motion or not, doesn't matter. But if the wave source moves towards the observer, the apparent wavelength is given by this equation. If the wave source moves away from the observer, whether the observer is in motion or not, doesn't matter. But if the wave source moves away from the observer, so O1 is here, whether he is moving left or right is doesn't matter. But the wave source is moving away from the observer, the wavelength is given by, the apparent wavelength is given by the first equation. Okay, by using these two, we can find the apparent frequency, whether the observer is moving towards the wave source or observer is moving away from the wave source. We can replace this equation by using plus or minus u naught. Say, for example, in this example, F2, I got the expression here. So, you know, observer is moving away from the wave source. You can see he is moving away from the wave source. So if the wave source is moving towards the observer and observer is moving towards the wave source, a situation where they are moving in opposite direction. Wave source is moving towards the observer and observer is moving towards the wave source. If they are approaching towards each other, what will be the equation for apparent frequency? So I can consider O2. So F2 will become equal to, in that situation, F2 equal C minus, so the observer is moving towards the wave source. So this, I got this equation by considering observer is moving away from the wave source. So put minus u naught over C minus US into F. You will get C plus UO over C minus US times F. So this equation is for when the wave source and the observer are moving towards each other. Okay, so what can be the equation for the wave source is at rest? Wave source is at rest, and the observer is moving towards the wave source. The wave source is at rest, and the observer is moving towards the source. In that situation, how to find? I can use the same equation. In that situation, I can say the wave source is at rest, so US should be 0. Observer is moving towards the wave source. I got this equation when the observer is moving towards the wave source. So there I can say F2 equals C plus UO over C minus 0 into F. That is C plus UO over C into F gives the apparent frequency when the wave source is at rest and the observer is moving towards the observer. So I can get all the apparent frequencies by using these two equations by substituting proper values. Say, for example, if the observer is moving away, I got this equation. If the observer is moving towards, substitute minus u naught, that is plus u naught, you will get the apparent frequency when the observer is moving towards the wave source. If the wave source is at rest, substitute US equals 0, you will get the correct equation for apparent frequency. So we can get all apparent frequencies by using these two equations. Okay, so the Doppler effect is due to the relative motion between the source and the observer. So if the source is moving on a curved path, you know that velocity is always along the tangent to the path, you know that. So if the observer is at rest and the wave source is moving along this path from P to Q, if that happens, when the wave source is at P, the velocity will be along the tangent, which is us. This is the observer, stationary observer. So the angle between the direction of the velocity and the line which joins the source and the observer is alpha 1. So the component of the velocity of the wave source towards the observer is us cos alpha 1. So we already derived if the source is in motion, observer is at rest, and if the wave source is moving away from, or sorry, if the wave source is moving towards the wave stationary observer, the wave source is moved towards the observer, the apparent frequency is given by f2. If the wave source moves towards the observer, the frequency is given by f2 equals c over c minus us. But here we should consider the component of the velocity of the wave source towards the observer. So only thing I need to replace us by us cos alpha 2. So when the wave source is at p, the apparent wavelength is given by this equation, c over c minus us cos alpha 1 into, f2 equal c over c minus us cos alpha 1 into f, and lambda 2 is given by, so I'm using 2 because it's approaching towards the observer. So lambda 2 is given by c minus us cos alpha 1 over c into lambda. The only difference is we need to consider the component of the velocity of the wave source towards the observer, or component of the velocity of the wave source away from the observer. So at q, you can use the equation. So at q, the wave source is moving away from the observer. So at q, I can say at q, it's moving away. So I can say lambda 1 is equal to c plus us cos alpha 2 over c times lambda. And f2 is equal to, f1 is equal to c over c plus us cos alpha 2 into f. If the wave source moves on a circular path at constant speed or whatever it is, but it's moving on a circular path, and if the observer is at rest at the center of the circular path, then what will happen? The velocity, will be always along the tangent to the circumference of the circle that has no component towards the center. The velocity, the tangent is 90 degree towards the component of the tangent towards the center is equal to 0. So the component of the velocity of the wave source towards the observer will be equal to 0. So if you substitute the component of the velocity of the wave source towards the observer 0 in these two equations, that is us cos 90, that is 0, you will get lambda 1 is equal to c plus us cos 90 over c into lambda. So cos 90 equals 0. So c over c will be 1. So lambda 1 equal lambda. Same way, you can see f1 also, the apparent frequency also will be c over c plus us cos 90 into f. Cos 90 equal 0. So this will become 1. So f1 equal f. So if a wave source moves on a circular path and observer is at rest at the center, always the observer will record the apparent frequency will be equal to actual frequency, and the apparent wavelength will be equal to actual wavelength. Okay, so next is about Doppler effect for electromagnetic radiation, or I can say the Doppler effect for light. According to special theory of relativity, the speed of the light about any frame of reference is the same. That means whether the wave source is moving towards the observer or away from the observer, or whether the wave source and the observer are moving towards each other, or whether wave source and observer are moving away from each other, whatever that happened, the speed of the light measured by the observer will be always the same. There is no change in speed of light due to relative motion between the source and the observer. That is the special theory of relativity. So, because of that reason, we don't consider the individual speeds of the wave source and the observer. We consider the relative speed of the wave source and the observer. So what we do, we can use one of these equations when we are deriving when we are deriving the equations for apparent frequency. For example, if I am using this equation, the only thing I need to replace UO or US by the relative speed of the wave source respect to the observer. So if I say the relative speed of wave source and observer is V, is V, I need to substitute one of it 0. Say for example, we derive this equation. Okay, speed of the wave source related to observer is V. So here this equation we obtained earlier for observer is moving away from the source and source is moving away from the observer. You know, relative speed means we take the observer is at rest, and relative to observer we measure the source. So in this equation I should substitute C minus 0 because I am measuring the speed of the source relative to observer. So I should keep, the relative velocity according to that. The concept according to relative velocity, I should keep the velocity of observer 0. Relative to him, velocity of the source is V. So C minus 0 over C plus V into F. That is C over C plus V into F. That is the apparent frequency. I need to find the change in frequency. So we'll find F dash over F, F dash over F, F1 over F equal C over C plus V. We know that numerator is smaller, denominator is larger, so this is less than 1. So I need to find the change in wavelength, means the apparent frequency is smaller. So we'll subtract 1 minus F1 over F equal 1 minus C over C plus V. Both sides I am subtracting 1 minus, 1 minus. So this is F minus F1, that is the delta F, change in frequency, over F equal C plus V minus C over C plus V. So this is delta F. Delta F over F equal C and C will get cancelled, V over C plus V. But when we consider the speed of the wave and the relative speed of the wave source, or speed of the wave source relative to observer, when we consider these two quantities, we know that speed of the light is the fastest. So C much greater than V. So C plus V approximately equal to C. So I can replace C plus V by C. So delta F over F approximately equal to V over C. This is the equation we use in electromagnetic radiation, for electromagnetic radiation related to Doppler effect. I can get the same format for change in wavelength in electromagnetic radiation. For that, I'm using the same equation. The source and the observer are moving away. So speed of the wave source must be replaced by speed of the wave source relative to observer. Because, I already told that there is no effect whether the observer and the source are moving towards each other or away from each other. The speed of the light will be measured as same according to special theory of relativity. So US must be replaced by V. So lambda 1 is equal C plus V over C into lambda. So lambda 1 over lambda equal C plus V over C. This I can write 1 plus V over C. C over C is 1. V over C is written already. So this I can write lambda 1 over lambda minus 1 equal V over C. So lambda 1 minus lambda over lambda equal V over C. Lambda 1 minus lambda is the change in wavelength or difference in wavelength, that is delta lambda over lambda equal V over C. So I can say delta F over F approximately equal to delta lambda over lambda equal to V over C, or even here I can put approximately equal. So this equation can be used only for electromagnetic radiation. Okay, so I hope you understood the derivations, all possible motions between the source and the observer I derived in this video. To make you to understand the applications, I uploaded a separate video with a question. So the link or the URL for that video is given at the description of this video. So you go to the description part of this video, there the link is given. So if you are interested, you can try that question. Okay.